Hey, my name is Austin Shelnut, and I'm with Strategic Thermal Labs. And for everybody who didn't have a chance to stop by our booth here in Atlanta, Georgia at Supercompute 2024, I want to give you a real quick tour of all the products that we brought with us this year. So right up front, we've got a couple of different cold plate types. Just kind of showing off that at STL, we are manufacturing in-house in our Georgetown facility a number of different options for how we can pull and extract heat from processors, all the way from extraordinarily custom to more mainstream parts to some things that are being utilized in labs today. If you follow me around, I'll try and keep this somewhat brief. First up, I want to show you our thermal test vehicle server. So this test vehicle server was designed to emulate the liquid-borne and airborne heat load profiles of the popular half-width, two-socket CPU compute server today. We have the capacity with this device to go and throttle up heat for CPUs and memory and NVMe devices independently of one another and emulate the heat profiles of those devices so that we can not only validate cold plate liquid performance, but also rack level liquid performance for things like CDUs and manifolds or row-based cooling solutions, in addition to rear door heat exchangers. This is the very first version of this device. It's not married to our cold plate. Anybody can install their cooling solution on there. In fact, you could use this same device for testing out air-cooled heat sinks. We intend to make multiple versions of this, and we have the capacity to go and respin the base building blocks of this design for anybody's hardware solution. So don't think that we're married to this particular form factor. We can go and make this look like anything that you'd want. The next version of this is going to be an 8-way GPU platform for more of the high-density compute applications. Right next to it, we have a device more designed for small co-location enterprise customers. It's a 1U rack mount ALC device, or air-assisted liquid cooling device. This building block has got 3 kilowatts worth of cooling capacity. It mounts in a rack right next to the servers, but it requires no backup rack manifold or pumping module. So you can take a liquid-cooled server and plug it directly into this box. And if you come in here, I'll show you a little closer. It's got liquid air heat exchangers, N+1 fans. We have a N+1 pump reservoir module here that uses 3 pumps, so we can have a 2+1 configuration, and an integrated flow manifold in the back. So any liquid-cooled server that you buy that has common quick disconnects, like UQD as an example, will plug directly into this module. We can scale these up and have multiple ALC devices for one server, and an example where you have a very high-powered server, or we can go the other direction. We can have multiple servers put into one of these boxes. It becomes a very standardized box, high volume, low cost, easy to deploy. It mounts on the same EIA flange rail that your server mounts on. And again, requires no complex back-of rack cooling network to go and deploy. All right, so you want to follow me around? Next up is the STL CDU solution. So basically, we took the components of the coolant distribution unit that you normally see in a data center, and we discretized them into 2 different functional blocks. On the right side is the brazed plate heat exchanger. This is a 3U rack mount box that'll fit into a 19-inch rack. On the left side, we have our pump module. This is a 3U box as well. Together, these are a 6U combination. The heat exchanger inside this box is rated at 150 kilowatts at a 3 degrees Celsius approach temperature, which is pretty high cooling capacity. On the left side of the pump module, we have 2 pump drawers that are both redundant and hot swappable. A lot of CDU vendors talk about having redundant pumps that aren't necessarily hot swappable or aren't easy to hot swap. If you get a little closer here with me, we'll go through. These pump drawers are extraordinarily easy to pull out. They can be replaced, worked on, whatever the service requirement looks like for the end customer. They have dripless quick disconnects in the back of the tray, along with a power cable and leak sense wire. The pumps we use are PWM controlled, so we can vary the speed of the pump dynamically based upon demand in real time. And then the pump cord goes back into the enclosure. And just like that, the new pump is installed. The chassis that these move into is called the MRC, or Modular Rack Cooling Device. Follow me back here. We've got hot swappable redundant controllers. We've got redundant DC power supplies. And then we have integrated differential pressure, flow meters, and leak sense in the back of the chassis as well. One of the cool things that, the reason why we decided to go with a modular approach for our CDU as opposed to a monolithic design is that we can actually create different relationships between heat exchangers and pumps based upon a customer's needs for redundancy or cooling capacity. So we have some customers that are adamant about having N+1 or N+N redundancy on their pumps. We can accommodate that simply by scaling up additional MRC boxes with our LLC box right here, the bracelet heat exchanger. Conversely, if we have customers who want to be extraordinarily aggressive on approach temperature with our CDU, we can increase the ratio of bracelet heat exchangers. This same design can be integrated into one rack, so we can take 8 of our bracelet heat exchanger boxes and 8 of our MRC boxes in a standard 48U rack, 600 millimeters wide, and create a 1.5 megawatt row-based CDU solution at a 4 degrees Celsius approach temperature, which is pretty aggressive. Follow me over here. So we're selling CDU solutions, but we're also leading the charge on a new type of cooling called bare metal liquid cooling. Bare metal liquid cooling is a non-CDU cooling solution where we design the cold plates and the rack infrastructure to operate directly on facility water supply, bypassing CDU entirely. This type of cooling solution is not for everyone. This type of cooling solution is for data centers that have fairly advanced water quality control mechanisms already in place in their facility or intend to get there. We believe that the CDU, while a necessary component of liquid cooling today, ultimately represents a fairly large thermodynamic parasite in the thermal resistance stack from a processor to the outside air. Our goal at Stream Thermal Labs is to eliminate thermal resistances, and from a thermodynamic perspective, getting rid of the CDU has significant benefits for being able to increase water temperature in the building and increase energy efficiency in the building as well. So this cold plate was designed using our distributed impingement recovery manifold technology, which allows for us to create a much larger channel with a hydraulic diameter of 600 microns and allow facility water to move through it freely without causing any long-term degradation issues that might possibly occur with a more sensitive cold plate. Now, I just want to say, we also make cold plates that are designed for CDUs, and those cold plates we can get down to a 50 micron channel, or a micro channel. These are 600 micron, so they're designed so that you don't have to worry about solid particles fouling up the fins. They're also designed to operate at 300 psi. So we've taken the approach, let's design the cold plate to be in the worst case conditions, both from a water quality perspective, from a solid particle perspective, and from a pressure perspective that a building might possibly throw it. Just to my left here, this is the same chassis that we use for our pump module and the same hot pluggable drawer, but for a bare metal installation, we replace the pumps with a filtration unit. Inside of each drawer, we've got very simple water filters, and these are 200 micron stainless steel mesh screen filters to gather out any residual particles that might possibly be in the water supply provided by the building. One of those filters, or filter trays, has got differential pressure monitoring across the tray and flow meters so that we can create a relationship for flow impedance versus flow rate, and send out alerts to a building to let them know if their filters are getting plugged over time. Expectation is that we've designed the filters and the channels of our cold plates large enough that most buildings won't have any trouble filtering their water supply below the point where these devices wind up capturing a lot of particles. However, there's going to be, in many cases, some startup issues where a building has built their pipelines maybe in advance of deploying their liquid cooling solution, and those pipes, if they sit stagnant for a long period of time, might have some scale that breaks loose initially, winds up in the filters, you replace the filters, and then probably never again over the lifetime of the product. All right, you follow me around here. The next thing up on our list is our rear door heat exchanger. So STL has taken kind of a unique approach to designing a rear door heat exchanger. Unlike most vendors who are using EC fans or centrifugal blowers, we are using 48 volt DC fans. And I'll open up my door here and give you a little closer look. This is 36 120 by 38 millimeter fans operating at 48 volts. That provides us a number of advantages, but it turns out when you try and do a parametric optimization of the coil impedance, the server impedance, and the ability to push airflow through the door, we wind up operating at a much higher mechanical efficiency point by using DC axial fans than what is possible to achieve with an EC blower. Consequently, that has other nice benefits. One of them is that we can use commodity power supplies that are common in the server industries that give us AC to DC power conversion and do so and also provide redundancy without requiring an automatic transfer switch. So all of our fans are powered off of the DC circuit, and our power supplies are commodity units that can be easily replaced. Each one of our fans is hot pluggable. Fan module comes out, it has a blind made electrical connector in the back of it, it can be plugged right back in. Objectively speaking, about the easiest replaceable rear door heat exchanger fan that you'll probably find on the market today. All right, if you'll follow me into the back of the rack, next up I'm going to show you our intelligent rack manifold. That's what you see back here. So our intelligent rack manifold, if you want to zoom in a little bit here, we have a circuit board that sits underneath this bezel, and you can see our RJ12 connections on there. This allows for us to collect liquid telemetry from each one of the servers that are currently being handled by the manifold in the back of the rack. So we can collect information like inlet temperature, outlet temperature, case temperature of the cold plate, leak status, and push that information back up to our top of rack controller and use that to make decisions on flow rates that are allowed to go through the manifold. Additionally, we have other versions of this same manifold where we can put flow control valves at each individual server location, and if we happen to have a leak incident, as an example, we can turn off water and isolate it into that server without impacting the rest of the rack. This gives us the ability to do closed loop feedback on component temperatures, so it's important that, as liquid cooling grows and scales, we need to stop overcooling devices and actually start cooling them based upon real-time consumption. And without the ability to extract processor temperature data and use that to control pump speeds and valve settings, we're always going to be in an open loop environment that wastes power. So, so that's our back of rack manifold. If you'll follow me around. So this rack is the first TTV rack that we've built here at STL. It's comprised of the same thermal test vehicle server that I showed you over on the other bench. This rack, we can put up to 40 of the thermal test vehicle servers in it. This one currently has 38. At the bottom of the rack, we have our liquid-to-liquid heat exchanger and our pump module. Now, what's cool about our TTV server is we also developed a dashboard operating system we call Thermopolis, or ThermalPal OS. And that OS dashboard allows for us to control each one of those TTV servers independently or as a giant batch and create dynamic load profiles. So we can go and vary processor power and memory power and NVMe power all by scripts and create various time versus power relationships and test out the liquid cooling system that we're working for. That's ideal for us to be able to test the rear heat exchanger capability, the CDU capability, maybe even the entire road network capability. So we can, from one dashboard, control up to 250 thermal test vehicle servers with the capacity to scale beyond that if required. So this is our first time at Supercompute. Really appreciate you tuning in. Sorry this video probably turned out a little bit longer than it was supposed to. If we haven't had a chance to meet in person, and anything that you've seen here is something that you're interested in, please reach out. You can go to www.strategicthermal.com or email at info@strategicthermal.com. Thank you.